Hello everybody. So my name is Hiroshi Makoshi. Welcome to web lecture of Engineering Science of Osaka University. I am a professor in the Chemical Engineering Department of the Graduate School of Engineering Science and Osaka University. So our laboratory's name is Bio-Inspired Chemical Engineering. Today's talk is much more related to our laboratory. So I would like to talk about the bio-inspired chemical engineering. Subtitle is use nano self-assembly for the next manufacturing. That is the subtheme. So first, I would like to talk about the engineering part of today's lecture. First of all, so I would like to talk about the rugby. I love rugby. So we Japanese and almost all Japanese people enjoy the big rugby game. So World Cup 2019. So when I used to play rugby when I was a high school student. However, so my body is a little bit larger than the other Japanese student. That's why I always play here as a front. So I always do like this. So I love rugby. So I love the concept of the one for all and all for one. So by creating a scrum, so we can induce the emergent physical power to move forward against that enemy. So that is my favorite. Please imagine that scrum of the molecule at the interface is also similar with the scrum of the rugby game. So in the biological system, there are many kinds of amplifiers. So amplifier is a possible player in the biological membrane. So maybe you can see this is amplifiers. So amplifier means a water compatible part, oil compatible parts. So both parts are accumulated in the one molecule. So that's why. So please imagine that. So our body consists of the 60% or 70% water. That's why we always face in the water environment. Please imagine that if you put these kind of amplifiers into the water system, they are not stable. That's why they are always try to create this kind of molecular assembly, just like similar with the scrum of the rugby. So by using this kind of scrum of the molecule at the interface, we believe that maybe we can induce some emergent properties. So similar with the one for all and all for one. That is a key concept of our research. Today's contents are summarized as three terms. However, before that, I would like to talk about the concept. Concept is a one for all and all for one. And also I would like to talk about the engineering part, science part, and also engineering science part. So in the first chapter, so I would like to talk about some engineering part. We are chemical engineering. That's why I would like to talk about the chemical engineering. After that, so I would like to talk about the concept of the bio-inspired. Secondly, so I would like to talk about the science. So basic science is molecular self-assemblies science. That's why so I would like to talk about the character of liposome. Why we selected liposome. I would like to talk about it. As finally, so I would like to talk about the engineering science. I belong to the Graduate School of Engineering Science. That's why I always think that engineering science concept is very important. That's why by utilizing our cutting-edge research, I would like to talk about the engineering science, by focusing on how to use liposome in the chemical factory. That is today's content. So I would like to talk about the chemical factory. Maybe if you visit the Bay Area of Osaka, so maybe you can see this kind of chemical factory. Many kind of factory are built around the Bay Area. So we are chemical engineer. That's why mission of chemical engineer is how to design, how to develop, how to control these kind of chemical factories. However, so there are many kind of remaining problems. So important issue is waste of energy and materials. That's why so we will have to solve this problem. So in order to do that, so new material, fantastic material, is very necessary to give the high yield of the product, high selectivity of the product. That is a remaining problem. So this is a schematic drawing of the chemical factories. Chemical factory is a combination of the different kind of unit operation. That's why so we will have to put energy, electric power, or also some labors power into that to manipulate these kind of chemicals. So as a result, we should put much energy or much material into these kind of chemical processes. And as a result, we can get a small amount of target product. That is problem. And also these kind of complex chemical processes can be roughly described as these kind of three terms. One is a mixing, and the second is a reaction, third is a separation. Mixing is easy, so very spontaneously they are mixed together. However, so reaction and separation is a very difficult to control it. So recent chemical engineer much more focus on how to control the reaction and separation. That is a conventional strategy. But so problem is remaining in the reaction and separation still. One big problem of the example of the problem is the chirality. So maybe if you look at the right hand and left hand, so maybe you can imagine the situation of the molecule. So there are two kinds of molecule, and left-handed and right-handed molecule. It's very similar chemical character. That's why it's difficult to separate with each other by using the chemical engineer's strategy. That is a big problem. So in order to solve this problem, so a scientist, chemist, or biochemist much more focus on the catalyst design, such as a Noyori catalyst, or also find out the enzyme, genetically engineered enzyme or something like that. And the chemical engineer would like to purify these kind of chiral molecules by utilizing the crystallization or chromatography. That is a strategy. However, so in order to separate this kind of material, so we should put the much energy, solvent or some waters or pH, acid, alkali, and as a result, so we should get such kind of separation process many times. That's why so we need much energy and much waste in the chemical processes. Once more, I can show you the chemical process design. So mission is a design and development and control, and we will have to solve this remaining problem, especially focusing on the chiral compound. If we could resolve this problem, maybe so this kind of complex chemical factory much more simplified. As a result, so we can save the energy or save the materials to put the chemical factory. That is a key factor. So among these kind of three terms, mixing is spontaneous. However, so as I said, reaction and separation is rather difficult. That's why by creating this kind of new fantastic material, we should grade up this separation to the much more grade up one, and reaction much more grade up one. That is our direction. So I would like to talk about the chemical factory and the biofactory. So as you can see, chemical factory you can see, and so by using this kind of chemical factory, we will produce some new chemicals, and we will create a separate target material from the synthesized material. However, so there is a big problem. So we always use the water and the oil to extract the target product. But as you can see, if you look at the interface, so problems are randomly located. And that's why so we should utilize enthalpy. That is the key factor. And also, this is a chemical structure, schematic drawings of the bacterial cell. Inside this microstructure, so they induce a very efficient, well-organized biochemical conversion inside here. So if you look at the surface, so they also have an organic phase and water phase and water phase, but there is big difference. In this case, so they are ordered, they have a highly ordered situation in the membrane. That is the difference. If we could utilize this kind of biofactory, and if we could utilize this kind of strategy of the biological system in the conventional chemical factory, maybe something would happen. That is our expectation. We call this strategy as bio-inspired. So However, so we have no determined the key material. So if we could find out the key material, maybe we can contribute to create a new type of chemical engineering. That is our key concept. And this is myself. So a little bit fat. No, I'm not sure. So I consist of the organ and tissue and cell. And if we look at the molecular level, so we are consist of the 60% or 70% water and iron, hydrocarbon, nucleic acid, protein, and lipid. So almost all biochemists and molecular biologists focus on this nucleic acid, trace level, protein 16%. So almost 99% research are much more focused on nucleic acid and protein. Please look at this. So 30%. So there are many abundant in our body, but so nobody take this important factor or not. So I would like to talk about the central dogma in molecular biology. So DNA information transcribed to create a messenger RNA, and the messenger RNA information are utilized for the production of the polypeptide as a translation pathway. And after that, so they created some folding, and they act as a catalyst, biocatalyst or antibody or something like that. This is a chemical structure, molecular structure of DNA, RNA, a little bit randomly localized, and the protein has a very well organized manner. So again, membrane. So membrane, abundant, so membrane components are abundant in the biological system. But so they are not think about the relationship between the membrane and the DNA, membrane and RNA, membrane and the protein. That is a problem, I think. Actually, we did many kind of research work, and so we keep this is important concept. However, so if we put the coexisting this kind of lipid membrane, sometimes abnormal behavior can be induced. For example, here, so this kind of protein, partly folded protein can interact with membrane. As a result, their conformation are defolded to the native state. Sometimes localized on the membrane, act as a membrane protein, sometimes translocated across the membrane. So in relation to the RNA, RNA has a random conformation. That's why so easy to interact with membrane. As a result of the interaction of the RNA and the membrane, so they control the gene regulation, upregulation, or downregulation, or something like that. Sometimes they act as an enzyme, because this is because of the a conformational change of RNA. Anyway, so all the phenomena relating to the membrane as a platform, we call this phenomena as a membranome. This is also our secret stance. Also, these kind of phenomena are discovered by our research laboratory, and this can be regarded as emergent properties of the macromolecule. Again, so this is a hierarchical structure, so we much more focus on lipid. So if we put lipid in the water system, they will create this kind of self-organizing system. They keep the nanometer scale environment. This environment is oil in contrast to the water, and they have a highly ordered situation in the nano-ordered environment. If we could utilize this kind of self-assembly nature, maybe we can get a fantastic material. So separation can be upgraded to the molecular recognition, and the reaction can be upgraded to the molecular conversion. Much better chemical process can be designed and developed. So key concept is the order of molecule in the given system. That is a key concept. That's why, so by utilizing, this is a comparison of the conventional system, oil-water system, and self-organizing system. So this is mainly driven by the enthalpy, and this is mainly driven by the entropy. That's why by utilizing this kind of self-organizing system with less energy, we can create a high efficient production. As a result, we can get a new type of innovation based on the self-assembly system. So answer. of bio-inspired strategy is a vesicle or liposome, self-assembly system. If we could utilize this kind of material as a key material, so maybe we can create a new type of chemical engineering, new type of factory. So this is also an overview of our research. This is a conventional chemical engineering. This is a conventional chemist or biochemist. Biochemists always create a new type of material and try to build up this kind of small material to create a nano-order material. Chemical engineer also always much more focused on the development of the much larger factory. But so we are always approached to the nano size. However, unfortunately, there is not so many research work in relation to the science of the nanometer scale. That's why we are now creating a new science, new type of science here. And after that, by controlling the order of the system, we should grade up this kind of system, and we would like to create a new type of engineering. That is key concept. So this is a rush hours picture in the Tokyo station. So everybody moving randomly. So that's why we can phrase as a 1 for 1 and all for none. So very catastrophic situation. So I love rugby, and so they created the order. In this way, so 1 for all and all for one is very good for the good game. Similar in the conventional factory and the new type of factory should be utilized this kind of self-organizing system.